Today I'm going to describe new capabilities that have been developed in the TRANSP code during the last 18 months. We have the following objectives of recent code developments. First, we want to improve our computational speed. For this objective, we focused on the new beam module for NBI heating and current drive by optimizing it for GPUs. The second objective is on improved fidelity, and we have achieved this objective while implementing the gyrokinetic models in TRANSP using T3D and JAC interface. The third objective is on improving efficiency related to software engineering. And we worked on implementation of IMAS to achieve this objective. IMAS brings a uniform standard interface to data and modules. The next objective is on modularity, and it's related to IMAS project. Because it's provide uniform access to modules, so it help the code modularity as well. We demonstrated that the modularity and use of IMAS interfaces efficient for code development by implementing new versions of TorBeam and new version of Toric for EC and IC heating and current drive. Another objective is related to code readiness for future project on machine learning and artificial intelligence. For this objective, I mostly will report about planning for future projects related to these topics. And finally, final objective is associated to so-called FAIR principles, which usually relate to data. However, most recently, there are FAIR principles developed for research software, and we will try to apply this principle to TRANSP code, and I will briefly talk about this as well. For my outline, I have these topics. First, I will describe the new beam developments. Then I will talk about progress in implementation of T3D and GX codes in TRANSP. Then I will talk about completion of IMAS transition and how it has been done and what is currently available in TRANSP. I will briefly describe strategic initiative working group activity. And finally, I will talk about resources available for users and how it relates to FAIR principle for research software. The outline is directly mapped to objectives of recent development in the following ways. It's quite natural that new beam work is related to improved computational speed. T3D and GX interfaces are related to fidelity improvements. IMAS project is related both the efficiency and improved modularity of the TRANSP code. I will start describing progress on optimization of new beam module on GPU. The new beam module is developed for a CPU platform. And in order to bring new beam code to GPU, there were significant refactoring and reorganization of code required. During that refactoring and reorganization, we discovered that significant improvement can be made without actually doing any additional parallelization in the code. So that while refactoring and optimization of module resulted in a factor of 12 improvement. On the plot shown on the right, the blue curve shows the original time as function of CPU for NIBIM module in TRANSP for simulation of D3D discharge, Super H mode discharge for 200 milliseconds with 160,000 Monte Carlo particles. After refactoring of the code, we get 12 time improvement, and that result is shown as orange curve here. In order to do GPU optimization, we actually need to move the code from Macune to a different machine, to Perlmutter, which is a supercomputer at NERSC. And of course, Perlmutter is somewhat faster, so it's actually that another improvement associated to just change of architecture. So the actual improvement associated to using GPU is shown in red, and we can compare these green and red curve showing improvement of factor at least 2, for some cases more. But most important is that because of this work of refactoring and optimization for GPU platform, we can run code at least factor of 20 faster. And for particular simulation for Super H D3D short for 200 milliseconds, we can complete simulation for 160,000 Monte Carlo particles within 16 seconds, which actually implies that we can do real between short analysis simulation within 1 minute, which is important. So it's high fidelity simulation with large number of particles that potentially can be used for stability analysis. And we can do parallel computation, just doing simulation at the same time for different ranges of time. At the same time on Perlmutter and kind of complete that simulation within 1 minute, which is important result, can be used for between short analysis for cases when we need to resolve distribution function at relatively high fidelity. So the next topic is on developing of interfaces for T3D and GX in TRANSP. TRANSP as integrated modeling code has a large selection of different modules that are needed to, well, for predictive and interpretive simulation. In particular, it has large selection of modules for sources for heating and current drive, including Nubium, Toric, Tori, Torbium, Gendre, SQL3D. It has number of free and fixed boundary equilibrium solvers, such as T, Q, and I solvers. It has models for large-scale events, such as Softus. For predictive simulation, it has pedestal models, more than one, including EPAD and several other models. It has synthetic diagnostics, so predictive simulation can be compared with experimental measurements. For predictive simulation, it has a selection of reduced anomalous and neoclassical models for profile prediction. And predictive simulation are done using PT solver, which developed as a modular solver. And because it's modular, so we can actually replace with some other solvers. One of such solver is T3D. It's Python solver that developed relatively recently. However, it followed path originally established by Trinity Code, developed in UK about 15 years ago. The advantage of using alternative solver in addition to PT solver and TRANSP that the T3D code has interface to gyrokinetic models. So it's provide embedded turbulence inside integrated modeling codes. In this particular case, in TRANSP, when it will be available. So first task was to verify if coupling scheme that we are using for coupling is stable. And in this coupling scheme, we send equilibrium geometry information as well as initial profile information for each individual time step to T3D, as well as sources. And T3D advances profile and sends that profile back to TRANSP. TRANSP again advance equilibrium, advance sources, and shares that information with Trinity. So basically, we had to ensure that our coupling scheme is stable. It does not lead to any numerical instability. And in the very initial step, we show that it does work. For initial step, we use jet discharge, this particular jet discharge, which is actually very old discharge. However, we specifically decided to use this discharge because, well, it was used originally with Trinity code about 15 years ago. Because the discharge is old, the diagnostic is not great, and you can see that ion temperature profile is not resolved in age region. So there is a flattening of green curve on the right. So in order to provide boundary condition to T3D solver, we need to set boundary conditions here. And for boundary condition, as typically we do in the cases when ion temperature measurements are not available, we set the boundary condition to electron temperature profile. So that boundary condition I indicated where the boundary is located in the simulation is shown as a dash curve here. And you can see that electron temperature profile is actually shown as a dotted curve here as well. Ion temperature is shown as a green curve, and predicted profile is shown as red curve here. So the test was not intended to match experimental measurement, but specifically intended to ensure that the numerical scheme is stable, and it was successful in that sense. After this successful test, we need to do more detailed verification studies of solvers if we have correct normalization of various terms. And it done it in multiple steps. The first step, we wouldn't have any sources or transport or collisional energy exchange term. If equilibrium does not evolve significantly, so we wouldn't expect any changes in profiles. So initial profiles should remain the same, and they indeed remain the same in TRANSP and T3D codes. The second test, we still don't have sources or transport. However, we allowing energy exchange, collisional energy exchange, when we advancing electron and ion temperature profiles, and there are small differences. However, that difference occur only when we send information for this collisional energy exchange from TRANSP to T3D, and that particular term is used inside T3D, and it's related to the fact that that term is computed from the previous time step, based on the profiles from the previous time step. However, when this collisional exchange term is computed directly inside TRANSP or directly inside T3D, profiles match exactly. So this test has been done with one impurity, and while we continue that test with two impurities. In this case, there are small differences, related differences in implementation of this collisional energy exchange term. So it implemented somewhat differently in TRANSP and T3D code. The next test, in addition to collisional energy exchange, also include sources that computed by TRANSP and sent to T3D code. And we claim that this result is successful, take into account that there are differences in this collisional energy exchange term. So basically, we ensure that the sources, all profiles are normalized correctly. So we have separate branch for T3D code that include interfaces for TRANSP at bit bucket. In addition to TRANSP interface, it also includes different alternative quasi-neutrality enforcement in T3D, and also support multiple impurities. Currently, we are doing another test that also send some information on diffusivity and supposedly use the same anomalous transport into codes. There is a user model in TRANSP that basically allows to set constant or linear dependence for anomalous transport in particular region, and so-called ReLU model in T3D. However, the ReLU model is what more sophisticated. It includes stiffness parameter as well as some minimal level of transport. However, it can be compared if anomalous transport in TRANSP is set to some constant value and stiffness in the ReLU model is set to 0. And in this particular simulation, where we're comparing the electron density profiles predicted with TRANSP and T3D, with sources computed by NuBeam and with particle diffusivity set at 5 meters square per second, both in TRANSP and T3D code. And results are close. However, they are not perfectly matched, and we didn't really expect any differences or significant difference in this simulation, in particular because sources should be exactly the same, and obviously there is no effect from collisional energy exchange here. Okay, so this work is still in progress. However, we can say that at this time, interface is currently available in T-share repository, T-share version of TRANSP. And I want to conclude this topic describing some consideration related to computational time. The JX code is specifically developed for GPU platform, so it's supposed to be run on Perlmutter. And JX code depend on the computational box as well as runtime to saturation of fluxes. The runtime also depends on the modes and instabilities that need to be resolved in that simulation. For a particular test for jet discharge that we tested in this initial studies, the individual time step in JX code is very short. So it's about 35 milliseconds per time step. In this case, we are resolving ITG modes, and total computation time for 500 normalized times in JX would take about 4 hours. Depending on the time steps that is set by transport time set, in this particular case, it's 1 millisecond, and time step is set automatically by TRANSP, and it's depend on the how fast the profiles evolve. The simulation, predictive simulation, can take really long time, and clearly predictive simulation not ready for between shot analysis. However, with some improvement, in particular, if we can reduce time to saturation inside GX, flux saturation inside GX, we can do interpretive analysis, flux comparison, stability analysis in between shot, depending on particular problem and a particular set of parameters. The next topic is on the progress on IMAS implementation in TRANSP. Why we are bringing IMAS to TRANSP? IMAS is currently international standard for data sharing. There are modules that have IMAS interfaces. Data are stored in Europe and Asia in IMAS format. All ITER scenarios are currently saved in IMAS format. Because we have this interface developed in TRANSP, data can be accessed from TRANSP and processed and saved in different formats. So it can be used as a way to access data. I'm happy to say that the project is successfully completed as of June 24. And what really changed for user with IMAS implementation? So I can say that IMAS is implemented as optional interface in TRANSP. So the users that prefer to use legacy interface, they can still use a legacy interface in TRANSP. Even TRANSP can be still compiled without any IMAS libraries. However, IMAS provides new capabilities. It has a way to access IMAS data, and it provides additional modules. I will talk about this for several RF modules that have been implemented using IMAS interfaces. During the project, we developed Python-based IMAS translator from TRANSP output. Currently, we are able to run TRANSP simulation either predictive or interpretive with inputs from IMAS database, and we can save some data directly to IMAS database while running the code. Larger option is available using this TRANSP to IMAS translator. TorBeam and Toric are implemented as part of IMAS project. And in particular, TorBeam module that has IMAS interface, its newer version maintained by IPP Institute in Garching, Germany, recently implemented in TRANSP. In order to verify the module, it has been implemented using old and new interfaces, and results are compared in this plot on the right. While we collaborated with TorBeam developers at IPP and at ITER to resolve name conflicts and proper deallocation of array inside TorBeam. Similarly, Toric 6 with IMAS interface has been also implemented in TRANSP using IMAS interface. However, in this particular case, we intentionally didn't remove Toric 5, so it's still available through legacy interface. And what is important is that currently Toric 5 and Toric 6 are available in TRANSP for direct comparison, and We believe that it's important because some different physics assumption and some different physics results from these two models. New RF models are enabled using IMAS interface, and in order to enable IC model, we would need to specify IC model equal to IMAS, and similarly for EC models, we would need to specify EC model equal to IMAS, and then TRANSP will look into IDSs, specific IDSs, and will try to find name of particular model inside IDS and to use that model. However, currently for IC and EC heating, there are only two plugins available for Torbeam and Toric. However, in general, this approach can be extended to other models such as gray code for EC heating and others. In addition, as part of this IMAS project, we developed a new tool which we believe will be very useful for FPP design studies. In particular, when we generate new equilibrium using iSolver, free boundary equilibrium model in TRANSP require pre-computed green function and mutual inductance matrices for coils and passive conductors. And currently, green functions and matrices need to be generated using make a QTalk tool during library build stage. This relies on pre-existing set of inputs for each device configuration, such as coil and conductor composition and geometry, circuit connection and feedback system, and iSolver numerical parameters. And basically, when we need to add new device or configuration, it requires some time from developer. The code needs to be compiled, the green function needs to be generated, and typically done during periodic release of TRANSP. New approach to make a QTalk tool allow generation of green function and related data at runtime. It uses all this information for coil, circuit, and numerical parameters from IMAS, mostly from PF active IDS. It offers faster turnaround and greater flexibility in configuration specification. It's particularly useful for concept exploration and FPP design studies. The next topic I want to talk about strategic initiative working group activity. Last September we had TRANSP workshops that outline several directions of future TRANSP developments, and that developments include improvement of interpretive capabilities and development of model validation platform. That activity would enhance model validation using Bayesian inference method and synthetic diagnostic. Another topic was on improving predictive capabilities, and specifically TRANSP users suggested to improve fidelity of models used for predictive simulation, and also use surrogate models that would improve computational speed of that simulation. Our technical task within strategic working group on improving fidelity and computational speed was specifically motivated by this recommendation. Another topic was on extension of transcode to the edge region. And in particular, we are looking into expanding TRANSP to the edge by providing Cork H coupling mechanism. The next topic was on coupling with engineering components. And this topic includes linking of TRANSP with engineering modules for virtual prototyping and advanced tokamak design studies. For all these 4 topics, we prepared white papers. However, more recently, we included one additional topic that was not really covered during TRANSP workshop last September. It's TRANSP for Oscar programs. And this particular white paper discusses use of TRANSP databases and modeling capabilities to drive breakthroughs in fusion science and machine learning artificial intelligence by enabling innovative data-driven research. And I want to talk about this particular topic because it's new. There are potential several applications of TRANSP. The first one is on machine learning artificial intelligence model development. For this topic, we will provide platform for developing, employing, verifying, and validating of machine and artificial intelligence models that would improve predictive capabilities and optimize control strategies in fusion research. And there are recent examples such as implementation of ELM, triggering and feedback models and RMP feedback models for K-star in TRANSP. The next topic on the Bayesian inference, and it's closely related to one paper on the white paper on the model validation platform, the first topic on the slide. TRANSP could integrate Bayesian methods to enhance interpretive analysis, systematically incorporating prior knowledge and qualifying uncertainties. The next topic of possible TRANSP contribution to Oscar programs is on data management and analysis. TRANSP can facilitate the handling and analysis of large data set for fusion experiments, contributing to improved data-driven discovery. TRANSP can be used to develop and test new methods for managing, curating, and analyzing vast amount of scientific data generated by simulation and experiments. And finally, another topic that we are discussing is advanced networking for distributed science. TRANSP can support multi-institutional collaboration by leveraging high-speed networks for real-time data sharing and remote computation. The last slide that I have is on TRANSP resources. And it's, I want to start this slide by saying that we invite users to contribute to TRANSP. We currently changing our license agreement to make TRANSP more open. If you're interested in TRANSP contribution, please let us know to be included to TRANSP GitHub repository. In doing this, we are trying to follow recommendation of FAIR principles for research scientific computing so that research software will be fundable, accessible, interoperable, and reusable. The recent changes that are described in these talks are available in T-share version released last week. This version is 24.4. I should remind users that T3D GX capabilities are currently available only in Permuter because it's required GPU capabilities. If you want to be a tester of these capabilities, please let us know. We can include you to TRANSP repository at Permuter. There are resources available for use. First of all, there is TRANSP website. For PPL users, there is also, a Strategic Initiative Working Group website. Recently, we submitted a paper to Computer Physics Communication. It's currently available in Archive. There is a GitHub repository for trans support. If you want to be included to that Git repository, please send us an email. We also respond to direct email requests. However, we prefer to keep all requests at GitHub repository. We have weekly open office hours every Monday at 11 a.m. and Zoom meeting ID and password is here, so please join if you have questions and if you have suggestions. We have regular monthly meeting with research organization representative. However, that meeting is typically relatively narrow for only research representative from each institution. This completes my presentation, and I appreciate your attention to this.